Hello and welcome. My name is Fernando Hernandez from Decision Train. I live and work out of San Jose, Costa Rica in Central America, and I will be presenting during the next hour a model and a conference based on the idea that Monte Carlo simulation can be done for project risk analysis on top of Excel, on top of any type of model. Obviously, I'm going to be working an example, but the idea here is for you to be able to do this yourself. So you can build your own models, analyze the information, and somehow replace the weakness and the relative fragility of the infamous heat maps or color risk matrices, which are just a rough approximation to the quantification or the description of risks, in this case, on a project. So the idea that I have here for the next minutes is to be able to present this conference based on, first of all, demystifying the quantitative risk analysis as an obscure and complex and sophisticated tool. And I am going to show and demonstrate, hopefully, that this is a very practical and easy to use methodology that can be implemented really easy. Now, we're going to be working on the components of a model. Then we set it, the whole model up as an example. Once we have it, we run a Monte Carlo simulation on top of it, and out of the outcomes of the Monte Carlo simulation, we'll be able to evidently, and that's the core of the whole thing, be able to interpret results and make some conclusions out of that. We're going to deal specifically also at the end on the convergence issue. Why do we run 5,000, 10,000 iterations as opposed to only a couple hundred of them? And we conclude giving away all the resources that are available around here for you to learn how to use these tools and get some additional information out of. Now, first of all, I want to demystify the idea. What I'm trying to say here is that qualitative risk heat maps are useless. There is on my website here, if you were to download this would take you to our YouTube session, and on our YouTube session or channel, which I am making readily available for you at this point, you'd be able to see, for example, here on my YouTube channel, which is called Decision Train in English, all kinds of information and additional videos and models that we have here to share with you. There's also information, for example, there's a PDF file on this whole course. It's a 60-page document, which obviously goes into much more detail in order to get an idea of this particular concept we're detailing here. So there's 60 pages that will take you step by step on how to set up the whole model. We're going to be working here on a 60-minute basis. So that's already available. You just ask for that at the end of a presentation. I'm going to give you the information on how to share those resources and how to reach me in order to get that information. Monte Carlo simulation, quantitative risk analysis is not that far-fetched. It is easy. It is not complicated. I know the PMIs and the International Standard Associations on Risk will make it harder for you, and they've been telling that for years, that, yeah, Monte Carlo simulation is something difficult. That's why we propose qualitative heat maps, because these are expensive software applications, number one, and only statisticians and actuaries and rocket scientists are able to do Monte Carlo simulation. My statement of the conference, the underlying idea, is that it is not as such. This is easy, well thought of and well planned. This is a methodology that you and I can easily do on top of an Excel model. So Monte Carlo simulation is going to be demystified here, and we're going to be using a DT simulator software, which is no more than simply macro-based code that I have placed on top of the examples that I have. You can always go to the site dtsimulator.com, And you can, right over here, you'll see it. And out of here, you'll be able to download yourself this model and be able to somehow work it out, either now or with the conference downloaded as a video or later on. So the model we're proposing here is as follows. As you can see over here, I am proposing, let me just shift this view over here for you to have it larger. You'll be able to see here that this is a project risk structure of a model in which total risk has been split into several different components. We've got ourselves 20 different risks on your risk register, and they've been classified on these 6 categories. So for example, the technical category encompasses itself 4 different risks. Logistics is like 8 of them, and so on and so forth. 20 different risks on your risk register. This is precisely the same point, the same starting point that any qualitative risk map would have, which is to define, to identify, and to write that information down in what we used to call a risk register. And our total risk is that it is an aggregation of these risks altogether. Now, we want to include here a couple of important concepts that I'm sure you're already familiar with, which are the core components with which you start to build any type of risk analysis. And that is to be able to split your risk into the component of frequency or probability, also called, and the other component, which is severity or impact. So according to the different standards that there are over there, you'd be able to somehow count the number of events with, in this case, what we will call discrete distribution functions, which we will see in a second. And also, on the other hand, you would be able to somehow multiply or convolute this by the severity distribution functions, which are usually continuous distribution functions. With this atomization of the 2 components, we are able to then build a quantitative risk analysis model on top of your Excel. Now, in order to do so, the frequency distributions, the ones that count your number of events on an eventual model, are usually discrete distributions. You're going to be able to see here, excuse me, that with only counting 4 of these distributions, starting with a simple one, the Bernoulli, adding a couple of additional ones which are pretty helpful and powerful, the Binomial and the Poisson. And finally, adding another one which adds to the scope of high uncertainty to our models, the integer uniform distribution. We'll be able to have a collection of, I would say, adequate enough number of distributions for counting the number of events. That is, for describing the frequency of your distributions of your risks. On the other hand, we will count 2 different types of continuous distributions that will somehow quantify your severity, your impact. And I classify them in a couple of groups. On one hand, I consider the parametric ones, the ones in which you would have to provide, probably by getting some statistical information out of a statistician, a mathematician, an actuary, you would have to get parameters on a log normal distributions. Those are relatively simple because you would only require a mu and a sigma, namely a mean and a standard deviation, and or other distribution functions, the parametric ones, the continuous ones, which would require some other types of parameters to quantify. Namely, for example, the exponential, the gamma distributions. They are specifically used for very specialized uses. On the other hand, you probably knew about these ones, the expert opinion ones, the empirical ones, the ones in which you don't need to necessarily know a Greek parameter distinction in order to be able to define these, because in this alternative case, you would have the expert opinion to form these types of distributions. So for example, using a triangular and or ampere distribution, you'd be able to see whether to use any one of these distributions. Now over here, once again, on my YouTube channel and also on my DT Simulator website. You'd be able to download this 30-lesson, 120-minute video course for free that allows you to dig deeper on answering these questions. This is one of the most common questions people come across all the time: how to select a correct and appropriate distribution for the job. So we got it over there. We can select, you can see the videos for free, or you can also always hire us and we'll be able to customize this presentation for you. Now, out of here, let me just go at this point to leave the PowerPoint presentation away. Let me just go back then to my Excel spreadsheet. As you can see over here, I have already loaded an Excel workbook, which contains, as you can see over here, 20 different risks, the ones we mentioned before. And they have been classified according to the 6 categories we gave. So in that sense, each one of these risks is going to be, as you can see over here, be categorized, consider on one hand the frequency and on the other hand the severity. When we have these 2 elements for each one of them, we multiply frequency times severity, and as you can see here, for example, on column M, we have the multiplication of your frequency, how many times does that event eventually happen, times the severity, that is the monetary damage that it will eventually cause at each one of the frequencies we get. So as you can see, multiplication here, this is our risk, and when we get them all together, all these 20 of them, and sum them all together, well, I already have them summed over here on the outputs worksheet. So on the outputs worksheet, cell D2, you'll be able to see that you've got yourself model the summation of all of them as evidently all the ones on column M. If I wanted to specify my more specific subcategories, for example, I'm interested only on the technical risks, I have a conditional sum over here, which would be adding up all together all the ones that belong to the technical category. So this is just a matter of having here the model itself and over here the outputs that have been previously declared. For example, take a look at this model that has already been previously defined. You'd be able to take a look at the inputs and outputs. In this case, I'm just clicking on the Show Inputs and Outputs button on top of my DT Simulator workbook that can be downloaded from our site. And you'll be able to see all your inputs that have been previously defined and all your outputs as well. So if I wanted to navigate here to, let's say, environmental risk, just double click on that, and this will double click it and navigate directly to that output cell that has been previously declared. Declaring your inputs, declaring your outputs is easy using these 2 respective tools over here. Showing them over here will be as such, and being able to show them is what comes next. So let's take our first risk and see how does this work. So the first risk is unknown site conditions. You go to your engineer in charge of this part of your project and you ask her, can you please tell me how likely this event is to happen? So she would tell you, well, every now and then, I would say once out of 4 potential experienced historic projects I've been involved with, I came across this type of risk. So she is essentially telling you 1 out of 4 is essentially 0.25 probability of having such an event. In this case, we would use a Bernoulli distribution. Bernoulli is the simplest of the distributions because it only allows for 2 possible outcomes of nature. The event either happens or not. It's a binary distribution. Take a look at how this distribution is being charted if I were to place myself on top of cell G2, which already contains this distribution. This comment over here, as you can see, just by hovering on top of that cell, I'd be able to see now that this is a distribution that generates a 1 in 25% of the cases according to the probability of success P equals 0.25. And on 75% of the cases, it would generate a 0. So in other words, if I were to simulate, that is, randomly generate events out of that cell, you'd be able to, taking a look at cell G2, you'd be able to see that once on the overall run, once every 4 potential recalculations, I am getting a 1, and 3 out of 4, I am simply getting a 0. The event, the risk, does not happen. That's what this Bernoulli is doing on top of the cell, generating randomly, according to this P distribution, either outcomes of zeros and ones. Now, imagine that this is a poorly recognized or studied type of risk. There's a lot of uncertainty. In this particular engineer, she doesn't have enough information to give you around a narrowing central point of what this outcome would be in terms of severity. She would only be able to give you, for example, information on the minimum parameter and on a maximum. And those 2 parameters are enough for me to build a uniform distribution, and it's also called a maximum uncertainty distribution on top of that cell. So this cell, which I could also always write down, remember that I can just place myself on top of the cell and write this cell or any one of the other DT functions as any other DT, as any other Excel function in Excel, just press or write an equal DT, and then in this case I would choose a DT uniform distribution, making reference to those 2 parameters, 400 as a minimum, 800 a J2 as a maximum, close parenthesis, and that cell would then look like that. I am therefore generating random numbers on top of that cell, and see how does the cell change on a value between a minimum and a max every single time I recalculate. I am randomly generating different possible, very uncertain outcomes on unknown site conditions if this event were to happen. Now remember, this event only happens on 75% of the chances. So on 75% of, only happens in 25% of the chances with the 1 here. So as you can see over here, this cell on 75% of the time would be a 0. Anything multiplied times 0 would be 0. But every now and then, this cell becomes, for example, 1 event, 791 becomes 791. So this is a very simple type of risk, a binomial, a Bernoulli type of risk, an either or, a binary type of risk. Let's try to elaborate a little bit beyond that. Let's go, for example, to risk number 3. Risk number 3, it's been categorized on its frequency by a Poisson distribution. And take a look at the nature of this risk. Damage or theft to equipment and tools. Certainly, just by analyzing the nature of this risk, you'll be able to notice that this is not a binary one. I mean, damage or theft to equipment and tools is something that could happen more than once during the length or duration of this project. So you go to your engineer, your field engineer in charge, and he will tell you, you know what? According to the security specifications of this project, the way that it's been fenced around the safety requirements, I would probably state to you that on average, this is an event that would probably happen 4 times during the duration of the project. Now, 4 is just an average on the mind of your expert. 4 can become 0 or 3 or 5 or 10. It's a number that eventually, on average, happens 4 times. Actually, as a matter of fact, you could have information on that. If I were to have a log of previous comparable types of projects, and out of that information, I came across that on average there were 4, then I would use that 4 as my single parameter for a Poisson. And take a look at how does this cell for frequency turn into. So if I were to start it as a blank cell and just write it down, equals dt Poisson, open parenthesis, making a reference to the only parameter required by a Poisson, close parenthesis, and voila. I've got myself a distribution function that looks like this. Yes, on average, the most frequent event is 4. As a matter of fact, it's also 3. because a Poisson would give you that the most likely events would either be a 3 or a 4, with approximately 20% probability of that outcome each. But then this number could tend into a 2 on approximately 15% of the time. It become a 1 in approximately 7-8% of the time. It become a 1 or 2% probability to becoming a 0, so on and so forth. So see what happens every single time I calculate now. That is, I recalculate and randomly generate events for that cell. The cell in this term, in this what we call an iteration, in this sampled number has become a 7. In this one, a 3. In this one, a 1. In this one, a 4. And so on and so forth. If I were to do this, let's say 5,000 times, then recollect that information and comprise that information, I may probably have something really, really similar and converged to this theoretical distribution of my Poisson. So this is a distribution that we use for counting events for frequency when we do not have, in this case, more than just an average. Now, let's take another example. Let me use, for example, this one. This one's really cool. Number 18, it's a different nature. Number 18, it's major damage to equipment. Imagine that you have on your field, among trucks and cranes and heavy equipment, you have 12 units. A couple of cranes, 8 vehicles, 8 trucks, and a couple of additional expensive machinery or equipment. So there's 12 of them. And out of your studies, and out of your previous either historic information on logs or your previous information based on the perception of an expert, the expert is able to give you the information that there's a 10% probability that any one of those equipments might eventually become damaged. And that information can be recreated out of probabilities, out of past historic information, whatever. We've got ourselves the 2 parameters required in this case in order to build a different type of distribution, a binomial. A binomial distribution requires 2 parameters. And those 2 parameters are respectively the units that are subject to the risk. In this case, equipment, trucks, cranes. Or there could be employees. For example, in this case, we've got ourselves the same one, or for example, over here, subcontractors. You've got yourself 30 subcontractors in which 5% of them are liable to become bankrupt. Or you have, for example, here another risk, which is currency fluctuations. You think that you might eventually have on average 3 currency fluctuations, and each one of them has a 15% probability of occurring. In this case, I've got myself 12 units, and each one of them has a 10% probability of being exposed to that risk. Take a look at the respective binomial. Let me show it to you. So that binomial here in particular is telling me that if you were to have 12 pieces of equipment and each one of them has a 10% probability of running into that particular risk, then there's approximately a 28% probability, I'm reading that as the height of this distribution, there's a 28% probability that you'll run into no events. There will be no damages. But then the most likely of them would be having exactly 1 damage, 1 risk, at approximately 37% of the time. There will be respectively approximately 23% probability. In other words, every single time I have 9, I recalculate, on 23% of the time, I may eventually run into a 2, such as in this case, even though the most likely scenario, as for example, in this case, is the 1, which runs into, in this case, 37% of the time. You would have to run this many times over to eventually run into 3s, 4s, 5s, and being very unlucky into 8, 9, 10s, 11s, and 12s. That's the nature on how frequency can be modeled with these 3 powerful distributions. Another one to add, probably the integer uniform distribution. Once again, we use the uniform distribution when there's a lot of uncertainty in which you'd be only able to give away 2 parameters, extreme, a minimum and a maximum, and then you'd model that with this integer distribution. In other words, there's, with exactly the same probability, possibilities of either generating a 1, a 2, a 3, and a 4 equivalently generated here probabilistically wise. So there's no way to reason here that this comes across as more likely or the other. Now, on the other sense, as you can see over here, for example, a log normal distribution would look like this if I were to use that distribution for that particular risk. In this case, a triangular distribution would look like this. This is a little bit slightly different. This is a triangular perk. A triangular perk is the same shape as a triangular, but in this case, the parameters are somehow differently placed. In this case, you're saying the most likely scenario is 500, and then there's a minimum variation of 500 minus 10%. That would be 450 as your minimum, and the maximum variation would be 500 plus 50% of 500. So that's 750. In other words, this is a triangular with the minimum of, as you can see here, 450, a most likely of 500, and a maximum of 750. It is just the same shape. It is only being expressed as parameters a little bit different, just because we admit that many people in the project practice do like the structure in which they think about, as an expert, of the most likely scenario, and then they just respectively assign probabilities to one side and the other on their distributions. So I think we're ready to simulate, see once again what happens at every single time I stimulate. In other words, every single time I generate random numbers, in this case for all the 40 moving parts of the model. 20 moving parts are these frequencies that I've already laid upon here. 20 other remaining moving parts are the distributions for the severities that I have over here. For example, I told you about the severities with a triangle, but you could have also done that with, for example, a PERT. A PERT distribution function uses, once again, the three conventional parameters of a minimum, a most likely, and a maximum scenario. Those three parameters being laid upon this cell, which stands as any other Excel function, same syntax, an equal sign, a name of a function, and then within parameters, in this case, the three parameters that define, in this case, the severity of damage or theft to equipment and tools. In other words, any one of the events of damage or theft to equipment and tools would have a monetary impact being stochastically described by this PERT. Now, there's all kinds of distribution functions for the severity, as I told you. There's, for example, one particular distribution here, the exponential one, which only requires one parameter, beta, which would make this distribution function with an exponential shape look as such. In this case, the mean, it's beta, $400 around here, and then most of the events, theoretically 68% of the events would be smaller than your average, and 36% of your events would eventually become larger than your average. The danger with this distribution, however, is that it extends to infinity. And think about it, the availability of construction materials, given, let's say, a strike or civil unrest in the country, might eventually mean that for practical purposes, the extension of this risk could go all the way on up to, theoretically at least, infinity. So those are the kinds of things that you start to model when you use a cadre of different distribution functions, such as the ones that we are proposing over here. Now, let me assure you, I've come across, and I've used for 17 years as a trainer and consultant for another company that made the most famous software for Monte Carlo Simulation. For 17 years, I consulted on these models and trained on these models. And for many years, out of the 90-something distribution functions, I barely used 13 available here. That's why on my product, those are the ones that I have made available. Just the most popular ones to make it a simple, easy to use tool in order to build your models. So I think we're ready to now simulate. And what is simulate? Well, automatically generate the moving parts, not once, not twice, not thrice, not any number of times, but in this case, remember, here on outputs, I've got my information, which is being updated every single time I generate random numbers. So in this particular scenario, for example, for total risk, I'm generating $11,000. For the next scenario, I'm generating $17,000 and $21,000 and 13 and 10 and 11 and 16 and so on and so forth. So someone comes and asks me, Fernando, what's your outcome? What's the answer that you should give? Shall you give a mean? Well, the mean is tricky because if I were to make decisions on the mean, then we wouldn't need risk managers or risk quantification at all. Because what you are interested, when you're interested on risk analysis, it's on the tails of the distribution. It's on the confidence of given information with a certain confidence or certainty level. And that's what we're achieving to do here through a Monte Carlo simulation analysis. A Monte Carlo simulation analysis is simply repeating this scenario generation, not once, not twice, not three times, but doing that all together many times. For example, for a starting point, let me start here with 1,000 times. So 1,000 times by changing a parameter over here, I'll come around here and simulate. Simulate means generating 1,000 times every single part of those 40 moving parts and their effects upon these 10 outputs which are receiving the information. I may say that information saving means moving the information from RAM into a fully declared Excel spreadsheet here in the model. So simulation has been saved. Therefore, if I were to go here to simulated data, I'd be able to see that, for example, cell outputs D2, my total risk, as you can see, has been defined here 1,000 rows down. 1,000 iterations or pictures or still photographs of what's happened to, in this case, total risk, and or also to my 20 moving parts, each one of the risks that I have. By the same token that I used by clicking on simulated data, if I were to click simulated data again, I once again hide that spreadsheet, which is the underlying raw material by which now I produce outcome analysis. In other words, these charts available here. And this is where we have finally arrived to a place in which now I can make decisions using the summarized information being provided by histograms. So let's take the first chart, the first photograph to our information. And that definitely will start with an analysis of a histogram. So I place myself on top of the cell that I want to analyze, either an output or an input. In other words, if I were to place myself on any blank cell and then go to histogram, the software itself will tell me, you know what, that cell hasn't been declared either as an input or as an output, so it won't be able to generate anything. Place my cursor on top of that cell and generate, respectively, its histogram coming across this. So let's stay here for a minute and analyze. So I've got myself and took 6 seconds to generate on my machine 1,000 iterations, and they've been somehow compressed here. Now, see the information being generated on 1,000 iterations or photographs or samples over here. If instead of that, I would have only generated, let's say, 100 iterations, and then just quickly generate a simulation on that. It actually takes a couple of seconds for me to get that information here. Take a look at the histogram. It barely reflects reality. There's a lot of holes in the information because 100 or 200 is a very small number of iterations to eventually converge. In other words, to eventually get a good representation of the reality of these risks. Even 1,000, as we just did, is relatively small number to generate samples. So in this case, let me use this and try to converge with more definite numbers than 5,000. Usually in our courses and for most of our models, we usually recommend on the question, how many iterations shall I use in order for my simulations to work? The usual, not necessarily for all cases, it's from something from 5,000 to 10,000. It's an adequate number for you to have enough data sets to converge. In other words, to have a really smooth out, nicely drawn curve which in this case for 5,000 iterations after 20 seconds would give me something of this better shape. Obviously, if you were to say 50,000 iterations, which is the max available here, you'll be able to have a much more smooth curve over here and make decisions out of it. Now, let's take information now out of the 5,000 iterations being generated here. So the minimum risk you'll come across as a minimum on $5,500 over here, which is this point or around here. As a max, you might as well go all the way up to close to $41,000. I mean, that's a lot of risk. If you were to consider the range of variation, there's close to $35,000 of variation around what could happen in your project. On average, and also as a median, that is your 50th percentile, the number is around 15,000. It means that around here on 15,000, this is the point of the most likely event. Now, remember that in order to consider confidence, in order to consider somehow the certainty degree in which we're making decisions, we usually come across with percentiles. For example, as a standard in international levels, I've come across that the 80th percentile, not that necessarily being the unique one, but it's become a standard in the construction, the civil engineering construction industry, using the 80th percentile on, let's say, large construction projects. You might as well have a different risk appetite. I've come across companies that work at the 70th percentile or at the 90th percentile, even at the 66.7% percentile. So there's obviously varying degrees of risk appetite over here. The other thing, which is a neat one over here, is the number of intervals we're using for drawing the chart. You could always change that to say only, let's say, 10 bins in order to come out across here. You don't have to simulate again. Take a look at the information now being categorized on only 10 different bins. It doesn't look like it's sharp. It's the same information. The simulated data is the same. As you can see myself here, I've got myself now 5,000 different rows. But then when I come across over here, it's been categorized and it's been placed on only 10 intervals. By default here, I would probably use something different. If I were to go all the way up to 100 bins as a maximum, this is just, once again, this is just a drawing categorization, 100 intervals or lines over here, in which you'd be able to see how the information has settled down over here. Now, we're talking about the percentiles. Percentile 80th is approximately $18,000. As a matter of fact, I could change that information exactly at 1780.87 once I've defined it. So I can place that as a target. So that level over there, that should be my 80th percentile. And exactly that, at 1780.87, my 80th percentile, 20% of the possible results would then be eventually larger than your 80th percentile. By definition, that's what an 80th percentile is. Now, I'd be then able to construct, if I were to know, for example, in this case, my median, which is, let me use a rough number, 15,000 as a close number here, for my vertical delimiter, the first one I've got over here. So I may just change it over here to this one, the target value number 1. That's the blue line we have over there. I don't have to simulate again. Take a look at the histogram. So I've got myself the first level here at 15,000, and then my second level at exactly the 80th percentile. What's the difference between this? Your contingency. In other words, now I can certify and say, ladies and gentlemen of the decision board, of the board of directors, if we were to construct a contingency for this project beyond the $15,000, at which we think would be the most likely, the expected scenario, the mean, then I would have to build a contingency, which is the difference between 18,000 minus 15,000, approximately $3,000. That's your pocket contingency. You would have to add on a reserve of $3,000 in order to be 80% confident that it will be enough to cover for your needs. Obviously, that changes. If a company works at a different risk appetite, let's say at the 90th percentile, I'd be able to change that information readily over here and read that my 90th percentile approximately comes across $20,000. In other words, if you want to be not 80, but 90% sure that you have enough contingency money here, so you should build a contingency allocation of not $3,000, but of $5,000. 20,000 minus your $15,000 over here. So imagine to pass from 80th certainty to 90th certainty, your percentiles, you would be adding 2,000 additional dollars to your 3,000. In other words, you would have to increase 67% your contingency money in order to guarantee 10% additional certainty on your results. So this is the major information you read out of your histogram. Information can also be read, for example, at this point, out of any one of the previously declared inputs. So if I were to be interested, let's say on this one, whatever, I can also read a histogram out of, for example, change order management, or read that out of natural disasters, and it would be read as such, and so on and so forth. When we, once again, simulate all the information, we've got that information not only for total risk, but also for any one of these. For example, logistics risks would look like that. And then environmental risk would look like that, so on and so forth. And obviously, I would have to change these two delimiters for each one of the cases, because I established these two delimiters for the previous one I read, which was the total risk, which obviously is larger in magnitude than the specific risks that I have. Now, the other level in which I can be able to do analysis would be here, my SCurves. Now, on the SCurves, you'd be able to compare using cumulative or percentile types of SCurves, in this case, all my risks, all my output risks. So, for example, here, it's the total one, but then you'd be able to see, for example, the cumulative shape of, in this case, logistics and environmental risk, which are going to be respectively the two largest ones that encompass your information here. This is a good comparison chart for you to compare with other distribution charts. Oh, by the way, this information, these JPEG files are being generated for each one of the risks over here. So you can then embed them back into your model. So that's been created automatically every single time. Let me approach the chart, which I consider the most important one from the managerial point of view of projects, and that is for sure the tornado. So I place myself on an output and I generate a tornado. What's a tornado? A tornado is no longer more than a representation of something called the correlation coefficient. In other words, the strength of the relationship of the variance of two variables, in this case between your inputs, the 20 ones we had on the green columns in column M, and your output, your total risk. So what's the relationship between them? Just by taking a glance at this chart, I can already make conclusions. 3 risks: availability of construction materials, number 1, and then the ones related to environment, natural disasters, and extreme weather conditions are the 3 risks that are going to be impacting the most my total risk management money over here. In other words, I don't have to worry too much about these remaining risks here at the bottom. If you had limited resources and managerial time in order to manage all your risks, I would certainly allocate my resources, my intelligence, my strength in order to somehow mitigate this information. Now, this model only allows me to go here to this point. In an hour, I don't have enough points and time to go into the allocation stage, the mitigation stage of what we want to do. But I already can say that availability of construction materials has the largest correlation coefficient against total risk. Let me take then a deeper look on what that 0.62 means. Okay, so I already know that it's availability of construction materials. In other words, this particular cell over here, my input, which is the one that is having the most impact upon this cell. So let me just place myself on top of my input, and on top of that, let me scatter plot it to total risk. And this is what I get. I get 5,000 scatter points on my scatter plot And as you can see, there's a straight line over here signaling the relatively strength of the relationship between my input variable, availability of construction materials, and my output variable, total risk. So as you can see over here, there's especially some very risky points, let's say beyond $15,000. There's going to be a handful of them, probably some 20 of them, in which if these extreme conditions on availability of construction materials were to materialize, then it would also probably and most likely mean that my total cost would also explode itself. As if I were to compare it to, for example, something smaller than that, let's say if I were to go to, once again, let me remember, on Tornado. For example, this one, incomplete designs and poorly defined scope, which as you can see is the least of my worries at this point. So this risk over here, if I were to place myself, draw the scatter plot of it against a total risk, take a look at the 5,000 compared points. I mean, there's a straight line. In other words, there's no incidence, there's no slope. As a matter of fact, the linear correlation coefficient is only 0.01. It's essentially 0. In other words, it don't matter what happens on your incomplete designs and poorly defined scope, because at the end, it won't have any impact whatsoever on top of whatever happens on your total risk, because it's the aggregated amount of my risk which I'm interested on. This is something in particular that can never be done by the heat maps. On heat maps, you can never add the reds or the yellows or the greens for that sake and add them all together and say that 2 greens stand to a yellow and 3 yellows stand to a red. It doesn't apply like that. You don't have that ability to build, and yet you do have it here because this is an aggregated model. You, by the way, you're adding all your risks upon cells here, which would allow you to get that information. For example, same thing can be done, for example, on logistics. I may place myself on top of logistics, generate, for example, a tornado out of that. And out of logistics risks, I'd be able to say, once again, this particular area of availability of construction materials is the one that has the most risk upon that. And that I can analyze. I've already done it so far here. This cell on its scatter plot to logistics risk, the category to it all belongs, you can see the straight line, the strong relationship in which this is an overpowering type of risk, availability of construction materials upon your total category of logistics risk. So imagine all the kinds of things that you could do over here. By the way, why this availability of construction materials become the largest risk? Well, its frequency has been labeled with a Poisson, which, and then once again, the Poisson probably has been turned off here. I can always turn that on here with the distribution charts comment, which now becomes available over here. We turn it on again. So you'll be able to see that's the frequency part, but especially in this one, it's a severity thing. And once again, as I stated before, it's been modeled with an exponential. And this exponential means that it will eventually, in very highly unlikely cases, become infinite magnitudes over here. That's what's happening over here. When I'm seeing the scatter plot with those extreme data points, it's essentially because I'm getting that information. Those extreme data points around here are obviously escalating me to a total risk, which is above, which are these very high levels that I have here so far. So far, this is what I wanted to present. I want to end my presentation. Let me just go over here to my PowerPoint presentation here. The other thing I was discussing, I've already discussed that with you. The number of iterations, see, and that's a convergence thing. See what happens when I only simulate here. I mean, this is 5,000 iterations. Take a look at, for example, my total risk when 5,000 iterations have already been drawn. Take a look at and take a look at, for example, this data. My 90th percentile is close to $20,000. My mean is $15,000. If I were to generate that, for example, with only 200 iterations, 200 iterations, by the way, is the limit on the student-free version of the software. You would probably conclude with very approximating figures, but then you probably don't want to present something of that sort to a decision making committee, for example. The information is roughly not the same. Here, we're almost escalating to 21,000 when it was 20,000. And then this might probably also be a little bit of the hook, as well as all the spaced extreme data points that you would eventually need to fill in somehow if you were to do this with a larger number of iterations to simulate. So let me just go back here to my last part of the presentation. So over here, you'll be able to, I'll just increase here. I won't put my presentation focus over here. Please do make the questions, especially by email. I'm making available here my email. I know there's always plenty of questions. I just don't have enough time to answer them here. I do welcome questions. I always love to answer them because it allows, obviously, to the starting of a relationship, which in this case, it's something that I want to somehow strengthen using these types of conferences and video webinars over here. Some of the, not some, I mean, the models we've already made available here are obviously available for you to use. So if you were to go here to DT Simulator site, dtsimulator.com, you'll be able to see all the products that are already being made available. Quantitative Project Risk Model is the one we're showing over here, the one we showed. Remember, each one of these models here, which you can always download for free, you don't have to pay anything here. The only restriction, once again, is that the maximum number of iterations is 200. But then any one of these models can be downloaded, as we've already made available over here, and each one of them comes along with the courses. So, for example, the one I'm showing today has Project Risk Model course, which is a free collection of, in this case, 12 YouTube videos, which will take you to understand at a slower pace, obviously, than what I attempted to do today on how to use the models or any one of the other models that are available over here. Now, at this point probably is a good time for me to come over here and start a poll. Let me ask some questions around. And the question I'm asking you for you to fill in at this point, please do tell me if you're interested on any one of those models. There's a basic cash flow NPV IRR model. If you're interested in a cyber risk model, this is not a single option. You can select more than one. And this is for me to be able to think on the next releases of the relative popularity of what we're finding over here. What is it that you're interested on seeing as conferences, as products, as PDFs? Remember that all this information we are somehow submitting here for you to see and to generate. So while this goes on, and I'm getting some reply over here, let me also add over here that we are also giving away the PDF document, as I told you before. So the PDF document is, let me finish the poll at this point. I think that's enough for you to see the results. There's definitely an interest in the operational risk model for financial institutions, but also in the basic cash flow model. And in relative terms, they come approximately in thirds, these ones here, for insurance, reinsurance, cyber risk, and other models as well. So it's definitely two strong ones and another one. As I was telling you also here, I'm also interested in showing you that we've got ourselves all this information being published also on PDFs. So if you're interested in having this material on a PDF, 60-page document that takes you with more calm, you'd be able to download it. Just ask to me, and I'll be more than willing to send it to you. And evidently, I make myself at this point available to you. Download the free student version, use the YouTube channel, purchase any type of template model if you're interested in presenting the results with more than 200 iterations. And over there, as I showed you before, any one of our products is available either in this professional version for 50,000 iterations at $95. And also you can have me, let's put it this way, for 3 additional hours for $250. So in other words, if you're interested in me coming with you and working on a specific model of yours, and you're interested in taking this to your project, to your company, to your team at your company, and you want to do specific customized either presentations or customizations of your model, tap me for that amount, and obviously we're more than able to do so. That's what we do for a living. So I think we have enough time for us to go in a couple of questions. Let me see if there are questions around. So people are asking some minutes ago, can we have the opportunity to replay this presentation, at least for those present? Yes, of course. The link is going to be delivered automatically to you, the link to this conference, which will give you that, a link to the Soho platform, which is where I've downloaded, but I am going to make it available also on my own platform. So you'll be able to even download it if you want to on top of your YouTube. I'm going to have it on my YouTube over here, but then also I'm going to have it for you to have it available on my platforms. And then I don't know, there is another question. I wanted to know how we should consider probability of occurrence of each risk. Obviously, Shervin, who's asking this question, this is a whole thing by itself. I try to tackle down somehow, as I told you before, on my decision train site, which is on the YouTube site or channel, which is called Decision Train in English. Over there, there's a specific playlist, this one. It's called Choosing an Appropriate Distribution. So choosing an appropriate distribution is a big playlist. As a matter of fact, take a look at all the lessons. There's 30 of them, 1, 2, 3, 4, with all these minutes. It's like 200 minutes, 2 or 3 hours, in which I give a specifically detailed description of each one of the distributions you want to use. So, for example, I answer here the question about comparing the PERT and the triangular. Which one shall we use? And I've got myself over here on the Bernoulli, on the binomial, on the Poisson. So there's more information over here for you to take a look with further detail over here. If not, once again, you can always go to the document here, the 60-page document, which is essentially the script that contains literally word by word what's been put up over here on the videos on my channel. By the way, this information is also on DT Simulator somehow over here at courses. You've got yourself all your courses over here on the different models we have, the basic cash flow model, the insurance model, the financial risk model, general help on DT Simulator. All that information is being. Okay, so that's it for today. I've taken, as you can see, that amount of time, the whole 59 minutes for you to complete. Thank you very much for your time. Once again, do not hesitate to contact me here at fhernandez@dtsimulator.com. Fully available to you to be in touch, to be of service, to provide additional consulting and training, to make these models work within your organization. And I'm glad to help. You have a great evening. You have a great afternoon. In any case, do have a great weekend. And thank you very much for your participation.